Over on the other side.
Well, our speaker today is Srikanthan, Srikanthan Sridharan received his master's degree in electrical engineering from the Indian Institute of Technology, Madras. He has worked as He's worked as a research engineer in Siemens Corporate Technology and later in General Electric, Bangalore. Currently, he is a PhD candidate working under Professor Krein in the area of loss optimization of induction motor drives. So we're grateful to have Srikanthan.
Thanks, Chris. Okay. I think it's not working.
Yeah, hold on a second. There you go. Try that. Try that.
Yeah,
There you go.
okay. So today's talk would be on induction motor drive design from loss minimization and damping perspectives. And I'm Srikanthan, and I'm a PhD candidate. I work under Professor Krein. And in about less than 3 weeks' time, I am giving my preliminary exam. So wish me good luck for that. And a part of this presentation would also feature in my prelim exam. So if you're too interested in hearing it another time, you're always welcome. So, okay, this is the outline of the talk today. The first one would be a small recap on induction machine drive loss optimization. I will exactly begin at the point where we left last time in the last fall seminar. So I don't expect you to remember what I did before, so I would just do a small recap of that. And then now we would go on to compare the system level optimization that we intend to propose with other minimization strategies that already exist in literature. And then the second part of the talk would have something different. Because of the connection of LC filters with induction machine drives, we observe a certain phenomenon which is resonance, and then we go on to develop an active damping controller designed for that to damp the resonant oscillations. Because these oscillations are very detrimental to the operation of the induction machine drive. And this active damping technique is not based on the connection of a physical resistance, which obviously incurs loss, but it does something else to damp these oscillations. And finally, we would see some of the preliminary results achieved by experimental investigation. And feel free to interrupt me at any point of time if something is clear or if I gloss over something that's really important. And at times, I may tend to become rapid because of my accent. So feel free to stop me. Okay. This is a typical nameplate of an induction machine. This is what you would see on top of the machine. So, but of concern today is the nominal efficiency. You see a NEMA nominal efficiency. NEMA is National Electric Manufacturers Association, and they always define what is called as nominal efficiency. This nominal efficiency is not everything. Nominal efficiency is the one defined when the machine is expected to operate under nominal conditions, which means I expect the machine or the motor to precisely operate around the nominal speed, nominal loading or nominal torque, and nominal frequency. So, but there is something called as running efficiency, which really depends on how we control the machine or how we operate the machine, which is really important. Now, why are we really concerned with running efficiency or dynamic efficiency? Now, we know that induction machine drives are quite popular in many applications. They are being used from end to end, which means that we have applications ranging from electric traction and automotive traction to even more electric aircrafts. And we have something called as drive cycle. A drive cycle is nothing but a curve of vehicle speed versus time. So this is precisely used by some of the governmental agencies and environmental protection agencies which do standard testing and emissions for an electric vehicle or a hybrid vehicle. So now I've just given two examples of drive cycles, which is an extra-urban drive cycle and New York City cycle. So you see that the drive is not really expected to operate at a constant speed, constant torque. You see that the speed is quite widely varying, which means the frequency of operation of the motor would also be widely varying. And now New York City cycle is pretty good. Now you really know what it means to drive in the New York City. So these have widely varying nature of speeds. Of course, they have widely varying nature of torque, which is dependent on how heavy the induction motor is, and then other factors like friction and then ramp and so on. But consider an aircraft application. The drive cycles are called as mission profiles for aircraft applications. In this case, I have shown the mission profile of altitude with respect to distance, but they are typically, we can also convert this into power requirements with respect to time. So aircrafts have widely varying mission profiles, which means widely varying speed and torque. So now how do we address system efficiency over wide range? That's the question we would like to precisely answer. Because most of the standard optimization, machine loss optimization techniques have focused on few driving points or nominal operating points and over not so widely varying range. So before that, let's see what the literature has really contributed towards addressing loss minimization perspectives in this area. So we can classify them into three categories. The first was material improvements and design methods, and Matt is working on one of those problems. So I really I am not quite well versed with these areas, just to mention that they exist. But what of concern is the control perspective, because dynamic efficiency is really governed by the control, because it largely depends on the control technique used. These two, material improvements and design methods, are primarily focused on static efficiency for maybe an extended range, and that is all about it. So even within the control category, we can classify them as online and offline controllers. So the online controllers are also called as search-based controllers. Now, if you have worked with perturb observe controller, this is something very similar to that. Let's say you can measure a certain input power which goes into the drive, and let's say you want to operate or control a certain variable, let's say flux, and then you want to minimize the losses in the system. So all you have to do right now is keep sensing the input power and change the flux variable till you reach the minimum loss. So that's the perturb and observe kind of a controller. But there are problems associated with that. Namely, one is the poor convergence, which means that they may not really try to go down to a steady state, but they can jump up and down quite a bit. And secondly, they may not really converge to the true optimum. That's also there, especially with applications like electric machines. The loss curve, as you would see, is not unimodal sharp, which means they have the minimum loss point is actually a kind of a tub you would see in most machines. So online techniques are not really successful in that sense. But offline have been implemented very well successfully in a lot of literature. And even within the offline techniques, we will, for the sake of discussion, we will concentrate on three major techniques, which are broadly defined, let's say, three major control techniques for machine optimization. So the first one would be machine loss reduction, which exclusively focuses on the loss optimization in induction motor, just the machine alone. And there is this maximum torque per ampere strategy, which is also called as MTPA. So this is about maximizing the torque for a certain amount of stator current. The next one is DC link current minimization. The DC link is nothing but the input source to the inverter, which is used to feed AC voltages to the drive. So now there are people who have concentrated on reducing the DC link current. But all three have a common factor, which is they have focused only on independent components, constituent components of the whole drive system. So some references here, which will be really helpful. And when we consider the induction motor drive as a system totally, we have this DC link, which we talked about earlier. We also have the inverter. Shown here is just a conventional two-level inverter operation, which is what is predominantly used. And then we also have the optional LC filters. Now the LC filters are definitely required for current source inverter-based drives. They are not necessary for ESI-based drives. But in the first in the first presentation I did a few months ago, I did the duality between voltage source and current source inverter drive, which means a voltage source inverter drive can be construed to be operating as a current source inverter drive if we map the control technique one-to-one. That was the conclusion of that presentation. The LC filter is now used to remove the harmonic components from the output of the inverter and produce a neat set of sinusoidal waveforms, one frequency. And the induction motor is here. So now let's go back and see the techniques in the literature. We'll just skim through them. The first one, this is quite very popular in the literature, Famuri and Cathay. They kind of had this extension of this paper, minimizing induction motor losses. So both concentrate only on machine loss reduction. So this, I'm sure all of you know very well, this is an equivalent circuit of an induction machine. This is the load resistance, the equivalent of the mechanical load. And there are obvious losses in the stator resistance Rs and the rotor resistance Rr prime. So now there are winding losses which can be easily modeled. The ID and IQ are nothing but the transformed variables in DQ domain. We don't have to really concern ourselves much about that because ABC system can be transferred into another coordinate system called as DQ reference frame, and you can compute losses even from that domain. And apart from the losses in the copper, there is also losses in the iron, which are the magnetic losses, and they have also been pretty well established using the Steinmetz and the hysteresis coefficients. So these can be characterized for the machine by doing certain tests. So now, obviously, when we have to compute the total machine losses, combine the winding losses in the copper and the magnetic losses in the iron, and then we have the total machine loss ready. So this literature is asking us to control the rotor flux variable. Let us call it lambda, and then the machine loss is plotted with respect to lambda, which is rotor flux, and you would see it's a convex curve. It's a nice convex curve with a unique minimum point. And then this paper is asking us to command this value of lambda optimum to achieve the minimum loss. So this is one part. But now it's very clear that it's only machine loss optimization and not beyond that. Now let's go to maximum torque per ampere. MTPS strategy can also be interpreted as minimum ampere per torque, which means to achieve a certain torque, the stator current that is put into the stator terminals can be brought down to a minimum. And when we write the machine equations in a certain format, in a certain domain, the developed torque can be written as this equation. It's the developed electromagnetic torque. KT is the machine constant based on the inductances, rotor inductance and stator machine magnetic inductances and so on. Lm is magnetic inductance. IQS and IDS are the components of the stator current. IDS is more concerned with the flux and IQS is concerned with torque. So let me explain this a little bit. Let's say there is a stator current vector shown here. You just drop down and resolve this into two components, which is the IDS and IQS. And let's take it for granted that they control the flux and the torque. So you can write the stator currents in this format. Let's substitute this in this developed torque equation, and it will be obvious that the maximum torque is achieved at 45 degrees because you have sine delta, cosine delta, it will be sine 2 delta, differentiate that with respect to delta, and that's very easy. And now this has also been extended by Guliang Zhang, who was a PhD candidate about 7 years ago, and this has been extended to improve power factor and efficiency, which means that let's not operate at 45 degrees, but some other angle which probably gives us a very good power factor and a very good efficiency. It need not be maximum torque. So that was the outcome, and then you can also see that there are certain angles at which there is maximum power factor and maximum efficiency. That was the conclusion. And so this is also concentrated on the stator current, which means at best this technique can probably bring down the stator losses and nothing beyond that. And there is also DC link current minimization. So this is the DC link. If it was a CSI drive, this capacitor or this bus would be replaced by a heavy inductor through which a constant current is expected to flow. And these inductances are quite huge, have substantial equivalent series resistance. So which means they incur quite a bit of DC link loss. And so there have been techniques which have evolved to reduce or minimize the DC link losses. That's what this paper is all about. And this has happened by the connection of LC filters. So now the idea is that by using value of a capacitance, a required value of capacitance, you can actually bring down the DC link rating of the inverter. Which means that if I reduce the current that is required out of the inverter terminals, it indirectly means the current that is required out of the DC link is also reduced. For power systems people, you can look at this perspective. Let's say you want to put additional capacitors to do power factor improvement. If you do power factor improvement, the net current that is drawn from the lines can be reduced potentially. So it's like looking at the same thing from a different perspective. And it has been proved that when you use the value of capacitance at LR based on this rule, you would get the inverter DC link rating to be the minimum. Now this is again reducing the losses in the DC link, but it's not focused on the whole loss optimization drive. So now it's quite clear that we have not addressed the whole total system loss problem formulation. So now let us take the total loss to be a combination of the winding loss, hysteresis loss, eddy current loss, the DC link loss, and the filter loss in the inductor, filter loss in the capacitor, and then conduction and switching losses in the inverter. So it's a comprehensive loss optimization. The only problem associated with this is it's not a very nice expressible form of an analytic function because of the complexities of different variables, but you can break them down as a function of capacitance and a control variable such as rotor flux. So which means the optimization outcome would give me what is the optimal rotor flux and optimal capacitance. This would be the outcome of this optimization process. And we fix two constraints. One constraint is the optimal flux can never exceed saturation, which is obvious. You don't want to saturate the machine. So you always put a limit on that. And the capacitance optimum is also restricted between lower and upper. Now, why do we have two limits for capacitance? The upper limit for the capacitance is because of size considerations. When the capacitance value goes high, the size becomes high, and the footprint of the whole drive system becomes higher. So which means we might want to avoid. And so that's why there is upper. The lower is because of THD constraints. THD is total harmonic distortion. So when you go below a certain limit of capacitance, you will see that the voltages become more distorted. They are not filtered very well. So that is also taken into account. So there is a C lower and a C upper. So let's say we put this function into a software like MATLAB and try to compute what the optimum point is, which we have seen before in the presentation. We just look at the simulation results and compare all the techniques. This has been done for two cases. One is the case of low loading conditions or light loading conditions, and the other one is for nominal loading conditions. Now let's look at the result. If we look at the drive system loss, it's quite clear that the system optimization results are, the losses are lower in the whole system optimization when compared to other strategies. And it's very clear that DC link strategy should never be used at light loading conditions because the losses tend to shoot up. That's the problem. But however, these are closer to this, but still, the system optimization seems to be definitely beneficial. And the reason for which is because of the optimum rotor flux profile. You can command a lower value of rotor flux when you use system-based optimization. And there is one more interesting observation. The green line, which corresponds to machine optimization, and the brown line is for the maximum torque per ampere strategy, that the flux is constant because the outcome of these maximization does not depend on speed. But this is a function of speed. The curves are all plotted with respect to speed. So now this optimization as system is dependent on speed also, and hence gives us the flexibility of bringing down the rotor flux at different operating points. So what does this optimum rotor flux profile mean? In order to achieve this minimum loss, if you operate your drive, let's say at 120 radians per second, this should be the flux that you have to command, and this value is the capacitance that you have to use. But now there is a problem because optimum rotor flux is easily achievable because it's just a control variable. In MATLAB, you just command that value and that goes into the machine, and the machine will take the necessary currents to produce that flux. But this is a problem. Optimum capacitance, it means that if the capacitance was variable, I'll have to provide dynamically varying capacitance, which may not be really feasible. But there is something to this. Let's look at the nominal question. Yeah.
Based on the previous slide, how do you determine the K1 through K7?
Oh, I'm sorry about that. Okay, I should have talked about it. The K1, K2 are basically weightage factors. If you really want, I have assumed all of them to be unity because I'm interested in true loss minimization. But if somebody does not want to dissipate more heat in machine, but he is okay to have, let's say, more heat in inverter, but less heat in machine, then you can weigh these accordingly. It's just like the LQR problem where the user can fix the weighting factors. But there could be a rigorous procedure where we could fix these factors, which may be a complicated analytical function, I do not know at this point. For true loss optimization, I've just assumed to be unity for all because I'm interested in the real loss optimization. So now this is a small bump which is just a rounding off issue. Otherwise the capacitance is almost constant. Now for nominal loading conditions, the system optimization is definitely effective because it results in very low losses compared to other techniques. But at very low speeds, it doesn't seem to be the most minimum of all, but in fact the increase is very small. Probably we can live with that. But for the most part, system optimization definitely gives better results. And if you see the optimum rotor flux and capacitance profile, they are constants for machine and DC link, MTPA techniques. But this is of concern to us because this is asking us to command or use dynamically varying capacitance. But if we do fix the value of capacitance, we cannot change it dynamically. So that's the bad news. But there have been literature which talks about dynamic capacitance. It's called as DCAP from Georgia Tech. And they have devised a power electronic arrangement wherein you can change the value of capacitance by switching arrangement. Now this would be obvious even in power system sense. It's like the static bar compensator wherein you would have capacitor banks and then switches, SCR thyristors. You can switch them at certain angles so that you effectively vary the capacitance that is needed in the circuit. It's similar to that. But there is some good news. We don't really have to dynamically vary the capacitance because we do a sensitivity analysis of loss. So what does this mean? We are going to see how loss is sensitive with respect to capacitance value. So 5 to 35 was our domain of interest in capacitance. We see that the losses within this range, 5 to 35, in these curves, the orange to red, are very close, which means essentially the drive loss is not that sensitive to the capacitance value. However, when we go beyond 35 microfarads, we do see that the losses go up tremendously. But that's not a problem for us because we have restricted our domain of interest to this. So as far as this machine is concerned, with these set of parameters, we will be okay with the fixed capacitance. And similarly for the nominal loading conditions. But there is one caveat here. How do we choose the value of capacitance? And since I'm given a range of 5 to 35. Now this is a certain judgment. You try to use the capacitance which gives the minimum THD, or if you are comfortable, or if the drive is, the THD is below the standard limits, let's say even for 17 or 18 microfarad, it's still okay. But this is just a judgment. So this can be chosen from any of this range. So now let's go to something a little different. We did see the system loss optimization and we conclude that system loss optimization is really beneficial. But now we also talked about the filters. The connection of LC filters has a certain issue. This has been addressed quite a bit in the past 10 years. That's because of the fact we connect the inverter output through the LC filter through induction motor. The induction motor is just a combination of, circuit-wise, it's a combination of many inductors and resistors. So there is an effective inductance and capacitance. And so which means there is an obvious resonance that can potentially happen. And this resonance is not the simple resonance as a series RLC. For example, if you all know, if you have a voltage source, connect by RLC in series, you, irrespective of the value of resistance, the resonant frequency is always 1 over root LC, which is the omega resonant. But the resistance here are quite strange, which means that you have resistances across the magnetizing inductor, in the rotor side, and so on. This has the effect of making your resonant frequency go around. It's not a fixed value. It's not 1 over 2 pi root LC anymore. This has been addressed as anti-resonant effect in the literature. So this is something that we have to avoid. But let's try an interesting analogy to this electrical perspective. Let's say this inverter is capable of producing a fundamental and a bunch of unwanted harmonics. This is similar to, let's say you want to ride a bike, a rigid bike with no tires on a cobbled street. Let's say like the Clark Street, which has bumps. So the bumps are the high frequencies, and there is a flat surface on which you want to course through. But now there is the problem of harmonics, which is these bumps. And so now we make it a suspension. So the tires. So now what happens is you get rid of the high frequency components and you still are able to go smooth on the road. But let us assume that the mechanical resonant frequency exactly matches the frequency of the bumps. We do not know how the Clark Street has been laid out, but it's very periodic. You know that there is a certain bump frequency for that. And if this bump frequency exactly matches or close to the resonant frequency of the mechanical system, the suspension would just oscillate very heavily. And now you would really wonder, why did you use suspension at all? You would probably prefer to ride like Flintstones. So now we have to get rid of this effect. So what we do is we make use of hydraulic dampers. The damper is a liquid inside the spring, and this goes up and down depending on the moment, and it dampens the resonant oscillation. And damping, we know electrically, is equivalent to inserting a resistance, in this case across the capacitor. But we all know from EC 101, introduction of resistance in a circuit is always lossy. So we would definitely want to prevent that. Because when we talk about efficiency improvement or loss minimization, we cannot afford to introduce resistors and then do a bad work at it. So we saw this, the suspension to reduce high frequency. And the literature has suggested something called as active damping. Now this active damping technique is a lossless technique. Let's look at how it has been implemented, only then it will be clear. You can ignore some of the loops here, they may be complicated. But what we are essentially trying to do is this. We sense the voltage, three-phase voltages across the filter, across the output of the filters, and convert it into VD and VQ, because we have VABC, convert it to VD and VQ. Now, let's assume a fictitious resistance, let's call it R, and compute fictitious damping currents called ID damp and IQ damp, damping in two axes. So now what we do is, we have certain reference currents to be tracked by the inverter for the motor. Without the filter also the motor will work, which needs a certain reference current IDS and IQS. But now since because of the introduction of LC we have this oscillation, now try to pull out or subtract the active damping currents from the reference current. So it's like a trick that the controllers play, you play with the controller. There is no physical resistance, but the control loop assumes as if there is some resistance in the circuit. So which means it's going to damp the system effectively. But this has been quite popular in literature, but there is no place where there is rigorous analysis of what the damping resistance should be. Because this value of the active damping resistance, the fictitious resistance, is very crucial, because that decides the transient and the steady state characteristic of the system for the drive. A wrong choice can be very detrimental. If you use a very low value of resistance thinking it will provide high damping, it's wrong. Because you would see that the resonance is much more pronounced. And if you use a very high value, you might not even get sufficient damping. So there has to be an analysis of how the damping resistance needs to be selected. And we also propose two more improvements on that. One, since this is only a fictitious resistance, you always have the ability to change because it's only in control. It does not really exist. Because if it was a physical resistor, you will have to fix the value at a constant and you cannot change it when the machine is operating. But since this is fictitious, it's only implemented in the control, you can always change the value of resistance according to the operation of the drive. And also there is one more advantage because of the breaking down of D and Q axis. If it was ABC, we would not have been able to do it because each phase has to see the same value of resistance, active resistance. But now, since we have VD and VQ, we can afford to have RD and RQ. And RD need not be equal to RQ is one proposal that we intend to make. So this has certain advantages which we will see in simulation. So now, how do we determine this active damping resistance value? These are the 5 equations that correspond to the nonlinear model of the induction machine without saturation. And then these are the nice equivalent circuits in D axis and Q axis. If you break them down into D and Q, this is what you will end up with. But this is just the motor alone, which is quite clear, and it's a nonlinear circuit because the state variables are clearly nonlinear. They are in multiplication, they are in product. And now there is the filter also that is converted into the synchronous reference frame. Because the induction motor is a mechanically rotating circuit, so it is brought into synchronous reference frame. But you also have the filters. The filter is a stationary circuit which is not rotating with the machine. So you have to convert the filter also into synchronous rotating frame, and that's why you see CF omega terms and so on. These terms come because of the effect of conversion to the synchronous reference frame. So let's say, you don't have to think too much about it, let's say we've got the circuit. So how do we go about finding the damping ratios and so on? As engineers, we know everyone would have done some control class. When you look at a circuit which is non-linear, the first thing that we tend to do is linearize the circuit. So let's go by the same method. Use a small signal perturbation. Let's have around an operating point, of course, because linearization can happen only about a point. So assume a steady state vector like this and perturb the variables using the hat. The hats correspond to the disturbances. And expand this equation. And since we have Mathematica, you really do not have to do it by hand, which is extremely tedious. So you end up with this kind of a matrix, which is neatly of the form x dot is ax plus bu, very convenient and very friendly. And now all you have to do is get the transfer functions that you require. Now we would like to damp the oscillations in the currents, ID and IQ. You could also do it on voltages, but I prefer current because that has the fastest effect on torque. So find these two transfer functions. And once we find the transfer functions, things are straightforward. And let's look at some of the simulation. Without damping, which means R is infinity in both axes, you see the gain margins and the phase margins of both the transfer functions. It's clear, it indicates closed loop instability because the gain and phase margins are negative. So that's a problem around this operating point. So this is only at this point. So now with damping included, this is not root locus, this is just a plot of the poles. We are seeing how the poles move with damping included. With R infinity, which is these points here, of course they are complex conjugates, so you should have poles here also. So you see that the poles are here, open loop. And the induction motor poles are stationary because they should not move because the induction motor is not concerned whether you add resistor or not. So, but when you add this active damping resistance, you see that the pole is shifting towards the left, which means it is giving relative increase or increase in relative stability, which is good for us. We want stability as a matter of fact. So this clearly indicates that use of damping is definitely helpful. And more the resistance that you include, the more left it would come. So now we earlier talked about question.
What is the VDW?
Oh, okay. VDW are and VQ are the outputs of the inverter. The inverter provides three voltages. Let's call VA invert, VB inverter, VC inverter. Transform it to DQ domain, that becomes VDW and VQW. W is inverter. So now we said that there are certain advantages using different values of RD and RQ. This is quite clear from here. At this the same operating point we considered before, let's look at the gain margin variation and the settling time. Now there could be a question, why gain margin and settling time? To have any control system that works, let's say with stability and also a decent time or dynamic characteristic, we need two specifications at least one from the frequency domain and one from the time domain. And now we choose gain margin from the frequency domain and the settling time for the time in the time domain specification, so that we will be able to achieve a decent level of stability as well as dynamic characteristics. So let's vary RD and RQ. Now it's quite clear in the gain margin in D axis, these two graphs correspond to the D transfer function, these two graphs to Q transfer function. D, the gain margin is dependent only on the D value. It's dependent on Q, but the coupling is very small. So the D axis gain margin is predominantly influenced by D axis resistance, which is good. And similarly for Q, the Q axis gain margin is dependent on the Q axis resistance, which means they are decoupled by themselves, which is something that we would want, because if you operate in a decoupled fashion, your control would be more effective. We use something called as field-oriented control, which is a vector control method. So it helps that. And settling time, the D is not very influenced by anything at all. It looks like a flat curve, except in this region, and even that is very small. Whereas the Q axis is definitely dependent on the Q axis resistance, the Q settling time. I really have not done any analytical work of why this depends on the Q axis resistance and why this is independent. Maybe I would do it close to my prelim exam, so I cannot answer any questions on that. So let's say that we have fixed from this curve, we can obviously fix what the damping resistances should be. Let's say we have come to that conclusion, what RB and what RQ has to be chosen for the active damping controller. Now let's implement it on a dynamic simulation with the real drive, with LC filters. The damping controller is turned on only at 0.25 seconds. Before that, you see that because of the damping, the resonant oscillations are very bad. And once the damping is introduced, we get rid of the harmonic components, and there is only the fundamental that is available in both the voltages and currents. And similar, the rotor speed was not really subject to much of oscillation before. It's a very small amplitude of oscillation speed, but torque, it's very bad. The oscillation is it's bipolar, which means it's shooting up and down, which is not good because of the currents. So the active damping controller has been proved to be effective. Now let's quantitatively analyze how much this improvement has been.
What do you choose to make the torque go negative 18 to positive 18? Like what was wrong before time of 0.25 seconds?
Because of the resonant oscillation, you use LC filters, and then you did not have any damping. Just pre-run the system with the whole system optimization we saw first. You think it would work, but the first optimization was only analytical. It was not implemented dynamically. When you implement dynamically, because of the capacitance resonance effect, you would start witnessing these oscillations. Okay? So we want to get rid of these oscillations. Please.
Like worst case, did you choose the values that were like the most?
Yes.
So it shows like the most dramatic.
Yeah, that's why I wanted to show it pronounced, and then so that it looks good. So now let's quantitatively analyze how much improvement has been gained by THT values, of course. Without damping, the THTs are very bad, especially in the currents. And with damping, we have brought down. There aren't standards for the, correct me if I'm wrong, I haven't seen standards for THT requirements for input voltages for induction motors. I haven't seen specifications, except in grid applications, there is IEEE 519, it specifies 5%. But I haven't seen an induction machine. But still, even if that's the standard, they have been brought down well under limits. This is the conclusion. Now let's look at the hardware setup. Since not many people have worked with hardware setup, I felt it would be a good refresher to go through what we really do in the hardware lab to test our results. So this is the overall block diagram. So this is where you would always see me sitting, the interface with the host computer. This is the power circuit. There is a voltage source inverter, coupled or the output of which is connected to an induction motor, and the dynamometer is like a load. It is a load in this case. It acts as a load for the induction motor, and this is controlled by a dynamometer controller for certain torque. Let's say if you want a certain torque as a load, you would command something on this controller so that it provides that load. So, and apart from that, the interface with host computer has the MATLAB code and models where you would use the, let's say, a code composer studio, or let me make it simple. You want to generate switching signals for the inverter, because the inverter is comprised of IGBT switches. So let's say this host computer is giving out the signals, the switching signals, and that goes to the DSP, and then it takes out and then gives out the switching signals through desired pins, which are connected to opto-isolation. Now, why do we need this circuit? The DSP output is only 0 to 3.3, which means an off is represented by 0 volts and an on is about 3.3 volts. But you cannot connect that to high power IGBTs because they don't work. You have to make them as power level switching signals. That's why we need a driver circuit. Convert the 0 to 3.3 volts into plus 15 and minus 15, which means turn on is by plus 15 volt and turn off is by minus 15 volt. And there is also opto-isolation. That's because all the switching signals are with respect to a common ground. But you really do not want a common ground to switch signals in the inverter because they are at different grounds. So you want to isolate them all. The previous generation used, some of the circuits still use what are called as pulse transformers, which give electrical decoupling but magnetic coupling. Similarly, the opto circuits will give electrical coupling but optical decoupling, which means the optics is the interfacing circuit. There is no electrical contact. So once we do that, these pulses can be sent to the switches of the IGBT. And now we should also monitor the voltages and currents because they will be used for processing to give out your commands and sense what is the torque, what is the speed, what are the stator currents and flux, etc. So we use a transducer circuit. The transducer circuit converts the high level or high power 300 volts 10 amperes to small voltages of about plus minus 5 volts. So this is given out with a transducer. But the DSP cannot accept bipolar signals. I mean the 2812 processor that we use, which means they cannot accept positive and negative signals. They can accept only positive signals. So you do level shifting, convert this plus minus 5 volts 0 to 3 volt. These are very simple circuits if you've done in analog circuits. Just make use of a bunch of op amps to do amplification or de-amplification and then level shifting. These are common standard procedures, nothing fancy here. So they will go to the DSP. And there is also protection circuit because just in case we run into trouble, let's say the voltages or the currents are faulty, then you always need something to protect or else the whole system will blow up. So you make use of a protection circuit to continuously sense all the voltages and currents and then issue a stop signal if there is a fault. If there is a fault, all the switches or all the signals are stopped to the inverter, which means the inverter is shut down. So predominantly, most of the times, more than a successful operation, we end up with a faulty operation. So let's look at the hardware setup in figures. This is the DSP that is being used. This is called as modular inverter. And thanks to the earlier graduate students who have worked on it for quite a bit. This is the big inverter module, which is mostly for research applications. It's easy because if you have to do anything with, let's say, implementation of control algorithm, you can make it as a modular inverter. But we made substantial changes to this because the gains that were there in the inverter were not right, and we had to fix quite a bit of components inside. It's a very good learning, I would say, if somebody is trying to do something like that. And signal conditioning circuit, power module is to provide all the plus 15, minus 15 powers to the whole opto isolation circuits and everything. And here are the capacitors, which we saw in the system level optimization. And there is a protection circuit for the current, protection circuit for the voltage. And this is the blue color machine is the dynamometer, which acts as the load. And this is the neat induction motor. Experimental results are not that very convincing, at least till this point. But even some preliminary investigations have revealed that it is quite fine. I mean, at least the concept seems to be verified. So this is at this operating point, and we are trying to plot the input power with respect to rotor flux. And this is the system without the minimization. There is no filter also. So we do not connect any filters and no minimization attempted. And when we do the system level optimization for using different values of capacitances, we do see that the losses go down. And there is one more agreeable fact that the minimums of these curves are almost at the same point, except this one, which seems to be an odd man out. But we have to repeat this experiment. But one thing that can be confirmed from here is system level optimization really brings the system losses really down. And the rotor flux is also, you can see that there is a change at which the minimum is happening, even though the minimum loss points are all the same. So experimental result for the system minimization, even though there are many rigorous assessments that have to be done. And these are the results for the active damping. Without the use of a damping, in fact, it can be much worse than that. I wanted to capture that was quite decent enough. So these are resonant oscillations because we have not made use of the damping controller. The same operating point as this. And once we introduce damping, we made them to be equal, but they need not be, so is what we concluded. So this was before we came to a conclusion that they can be different. So use same values of resistances, you get good results by doing the active damping technique. And time, please.
Time up.
Okay. Okay, that's all. I knew. Okay, so now let's conclude. I had some slides, many more slides for the next problem. So let's conclude some of the main takeaway points from this presentation. We conclude that system level optimization definitely results in more efficient drive than individual component optimization. And one important takeaway is system loss is relatively insensitive to capacitance value. And we have proposed a method as to how to select the dynamic resistance value for the active damping controller based on the transfer function method. And so this will conclude my presentation technically. And if you have any questions, I can take them right now or even any time later.
The improvement after you do the active damping, is it relative? Meaning, like, if it's really bad, it improves it marginally a little bit, or if it's really bad, does it usually improve it a ton, like going to where like this one is? Does that make sense?
Yeah, but there is only a certain limit with the controller because we have the DFP which cannot switch at high frequencies.
Okay.
So you would see that this is the best that can be improved for this set of conditions. But in theory, we can actually get much more smoother waveforms. In fact, no switching frequency harmonics at all. Well smoothed waveform, but that would require very fast sampling and then very quick computations.
Okay, so like the DSP that you used, had a limitation on what the group had, and so you used it, or did you pick that out?
The limitation is because the DSP is sort of coupled with a modular inverter.
Okay.
I cannot use a different DSP. So probably if we go for another better sampling arrangement and faster switching frequencies, faster frequency of sampling, it's definitely a possibility. But with this is probably the best that we can probably do an improvement amount.
Curious, the THD for each phase, it should be quite close to each other, right? Like I see some like 200 and 160 are quite off, so.
Right. Okay. This, when you take out the waveforms from simulation, you also have to sample from the MATLAB command window or even from the scope. So when you sample them and when you reach a steady state frequency, that would be the base frequency for computation of Fourier series. So there could be a few samples that are on and off out there. So you would see that even a few samples that have gone wrong, let's say if one cycle comprises 7,200 samples, and then you are able to extract even 7,196, the 4 samples is actually approximated by a kink or let's say a sharp curve when you do the sampling. When you run the Fourier analysis code for it, it assumes that that's a harmonic, high frequency harmonic. That's the reason why with all sampling arrangements you would not get identical THD values. That's because of the sampling arrangement. But in theory, they have to be the same.
Okay. Is it helpful if you run this a little longer?
I don't think running longer would have much or any big impact. But if we have a dynamic Fourier series, very accurate Fourier series computing instrument like a spectrum analyzer, which has extremely high sampling, then that's a possibility, I believe. Yeah.
Have you thought about the thermal effect on the components? Under different load, actually the passive components change their values because of the temperatures.
That's true.
That would be part of the optimization.
Yes. Okay. Thermal perspective has not been taken into account, but there is a possibility that you can accommodate that into the objective function as a thermal factor, but that seems to be more involved, so I didn't really go into that area for now. But it's true that the thermal considerations are also important because in the system optimization, you really do not know which component is getting heated up. You know that the net losses are coming down, but it could be that the inverter losses have come down so drastically, but the machine losses would have increased a little bit. So that, I think, may be a future work that has to be analyzed because inverter cannot tolerate high heat, whereas the machine, because of its thermal capacity, can tolerate more heat. So that kind of trade-offs can be done by making the objective function much more rigorous. Use the proper weightage, K values for each of the components. That's still a possibility.
Do you have any plots of poor choices of damping resistance?
Oh yeah, okay.
like slide 24 shows like very good results, but do you have one that's like
Yeah.
maybe 35 ohms and it's actually quite bad?
Yes. I think I have. Okay, I'm sorry. I have to acknowledge. So sorry about it. Granger Center for having funded most of my work, and Rolls-Royce for whom we are developing a small power flow model for an all-electric or more electric aircraft. Some of the last models that we've developed would probably fit into the last computation for the Rolls-Royce model that we've developed.
I'm going to interrupt you at that highlight there, okay? Every one of you, every talk you ever give should have an acknowledgement in it. Okay? Somebody's paying for your work, I think, in almost every case I can think of. Okay? Don't forget it. Don't make your professors remind you every time. Just do it.
Sorry, it was not an omission, but I had this after the backup slides. I'll see. Okay, I'm sorry, I don't have that. Okay. There are values which will result in poor PhD. All right. Thank you. If there are no questions, thank you so much.
Don't forget about the tech meeting, the conference room right now.
So it's going to be upstairs in 45 minutes too, and it starts in a few minutes.
Why